For the rest of the time, what we're going to do is use the principles that we've learned thus far in our physics class to try to calculate the muzzle velocity of a gun in as many different ways as possible. Now, today, the only kind of gun that I can possibly bring into class is this one here. Okay, there's some bills before the legislature that if passed, every single one of you will be packing, which makes me a little nervous at exam time. Anyway, if you wanted to calculate how fast the bullet was traveling when it left that barrel, how many different ways could you do that? Be creative. Talk to your neighbor. Come up with at least 4 or 5 different ways. I have to apologize. We actually were scheduled to have a lot more different demos today, but over the weekend, Jerry, who does our demos, was mountain climbing by himself and fell 30 feet and landed on a sharp rock. And so this morning, when I was expecting everything to be set up, next thing I know, Jerry crawls in on crutches, barely moving. Oh dear, oh dear. So he's not doing so good. I've come to appreciate just how important it is to have people that help to, set things up. So anytime you see Jerry, just thank him for all the work he does to make our class move so smoothly. What did we come up with? What ideas did you have for measuring this muzzle velocity? Raise your hands, because I'm still waiting for my hearing aids to come back from Costco.
Force times change in distance.
Okay, force times
The change in distance.
the change in distance. Okay, so if I could compute the force exerted by the black powder or the explosion and the distance of the gun barrel, that would work. Other ideas?
Using energy, the chemical potential energy of the explosive plus the gravitational potential of the ball.
Okay. So now the part about the chemical potential energy worries me a little bit, because we can dance when I know about chemical potential energy on the head of a pin. But you're right, if we had a formula for that, we could do it that way. What about things that we learned in this class that we've studied this semester?
Just do the time it takes from when you pull the trigger, when you fire and hits until it leaves the barrel. That's a delta X.
Okay, so if we now if we take that delta X as it's in the barrel and divide by the delta T, that's just going to give us an average.
Yeah.
And then what do we have to do to the average velocity to find the final velocity? Multiply by 2. Yeah, if we start from 0, the final has to be twice as big as the average. Yeah, so that would work. If we could measure that little bit of time that it was in the barrel. What if we wait till it gets out of the barrel?
Delta X and the time it takes between the two.
Exactly. So we know that if we fire it horizontally, the horizontal velocity doesn't change if we ignore air resistance. The vertical velocity changes by 9.8 meters per second every second, but not the horizontal. So if we take that distance and divide by time, what else can we do?
Wait for it to hit something?
What's that?
Wait for it to hit something?
Yes, we could have a collision with it. We just studied collisions. We could fire this into a block of wood and see how much it moves that wood. And that's the way they actually do it at FBI headquarters. What else would you think?
You could put it on a frictionless surface and look at the mass of the gun and the velocity afterwards.
Wonderful. Okay, if we have the standard frictionless surface, we just look at the recoil of the gun and we conserve momentum during that explosion. Whatever momentum this has, the gun has one way, the bullet's going to have the other way. Good.
Spring energy, so spring constants. And
Okay. In this case, would need a spring constant, but a lot of guns don't have springs. And so with energy, we'd have to go back to the chemical potential energy idea. That would work. Let's summarize some of these ideas that we've come up with. One idea that didn't get mentioned is just to get a motion detector, a little speedometer, as it were. And I think we can get rid of that plan because it looks dangerous. I found this on the internet, and I just want to say some people have worse jobs than yours. Okay, there are some jobs that are just not fun. That's going to leave you worried. So let's talk about the kinematics approach that was presented by this gentleman over here. If we fire the gun horizontally and measure the distance and then divide by the time, we would have the horizontal velocity, which is the original velocity. That's what it left the barrel with. Now that time is going to be hard to measure because it happens pretty quickly. We could also do it with only a meter stick. And we could do that by measuring the height. Now, if I measure just the height of the bullet when I fire it, and I use my kinematic equations in the y direction, so if I call down the positive y direction, then delta y is equal to v naught y delta t plus 1/2 ay delta t squared. Well, if I measure that h and I call down the positive y direction, delta y is going to be the h. It starts with no velocity in the y direction, so that term goes away. And what I get is 1/2, if I call down positive, this would be 9.8 meters per second squared, and then delta t squared. And that gives me a delta t of 2h over 9.8 square root. Now, let's try that. Let's actually get a muzzle velocity for this guy. Do I want to measure to the bottom of the bullet, the middle of the bullet, or the top of the bullet from the floor? What lands on the floor? The bottom. So I want to measure to the bottom, and that is going to be 107 centimeters. So the H is 1.07 meters. So I come over here and I take 2 times 1.07 divided by 9.8 and then square root. Someone with a calculator be calculating that while I find the range. Okay, so that's about right. And now we put Osama bin Laden, the guy that George Bush got. Oh wait, it was the other guy. Yeah, now I remember. The guy that gets things done. Okay, let's see. Oh. ho, that's some kind of aim. 2.6 meters. So L is 2.6 meters. Delta T is, what did we get?
Point 15.
Point what?
15.
I think point,
0.15.
0.47.
0.47 sounds right. Okay, did you square root it? Yeah, this sounds right. So that means a velocity of 2.6 meters over 0.47 seconds, or around 6 meters per second. Now, if you're working for FBI and you want to measure or calculate this muzzle velocity for a gun that was used in a crime, you don't want to go outside and fire it horizontally. That's going to cause problems. So what you do instead is you lean out the window of your building if you're in a high-rise. Oh, that's how you do it. And you fire the bullet straight up. And you have your colleagues on the upper floors kind of peek out the window, don't lean out too much, and see how high it goes. Okay? Now, if I take this gun and I put it here, who's got the bullet? Thank you. So now I fire it straight up, and if I know how high it goes, I can use energy conservation. At the bottom, when it leaves the barrel, if I call that height 0, it's got kinetic energy. When it stops at the top to turn around, it no longer has kinetic energy, it just has gravitational potential energy. If we ignore air resistance, then what we have is the kinetic energy leaving the barrel is equal to the potential energy at the top. We solve, if we know what H is, we solve for V. Okay? Now, if we had time to do that, what we would get is something very, very close to 6 meters per second. Now, again, most FBI agents are kind of hesitant to lean out their window and fire a gun straight up. Again, there's consequences. So instead, they do what we talked about, where you fire into an object, like a block of wood, and you watch as that block of wood gets pushed across a rough surface. Now, if you measure how far it goes, and you're able to measure the friction force by using a force probe and pulling that block along the surface at constant speed, you can solve for the muzzle velocity. First of all, during the collision, do you conserve momentum or energy? Momentum. It's a maximally inelastic collision. They stick together and move together. So energy is not conserved. It's momentum that's conserved. And here, I'm going to have, before the collision, it's just the bullet that has momentum. And remember, that's what I'm looking for, that muzzle velocity V. After the collision, the block and the bullet stuck together are moving at some final velocity V block. If I know what V block is, and I know how massive the block and the bullet are, I can solve for V. Well, how do I know how fast it's going after the collision? Well, I measure how much Verk is done, and I let that Verk steal the energy. Okay? So I look at the kinetic energy that the block has with the bullet embedded in it right after the collision. And then I look as friction takes that energy and whittles it down to 0 over a distance of delta x. If I solve that for V block and then put it into the other equation, I can solve for the muzzle velocity. Now, what's more common is for them to fire into what's called a ballistic pendulum. And in that case, you fire the bullet and that causes the pendulum to swing, and eventually it turns around to come back down. Now, the height at which it turns around allows you to calculate how fast it was going right after the collision. So again, if you use momentum conservation, you can find the speed of the bullet. Now, we actually had setups for these things, but as I say, I apologize that we didn't get to do that. On Wednesday, I am going to just practice to get you ready for the exam. And on Friday, we're just going to go over your graded exam. That's an optional day for you. You can come or not come. Okay, we'll see you on Wednesday, people.
Great.